Hello friends, in this video let us discuss about Thevenin's theorem. So the Thevenin's theorem is a very fundamental and important theorem in electrical sciences because it reduces the complicated network into a simple network. So in this video let us see how Thevenin theorem is going to reduce the complicated network into the single network, and we shall also discuss what are its practical applications. Suppose if you want to calculate the current flowing in any particular branch, let us say I am having a branch. This is my branch RL. Now I want to know the current flowing in through this particular branch, and this branch is connected to the rest of this circuit at its two terminals A and B. So this is your rest of the circuit. Now due to the active sources present in this rest of the circuit, an electrical potential difference appears across this branch. So due to this electrical potential difference, you are going to witness a current flowing through this. Let us say this is our load resistor through which we want to find the current. So due to the electrical difference, we can witness the current flowing through this load resistor or the branch through which we want to find the current. So now I can replace the rest of this circuit with a single voltage source whose voltage is nothing but the open circuit voltage appearing between these two terminals A and B, and the internal resistance of the voltage source can be considered or regarded as the equivalent circuit resistance by looking back into the circuit from these two terminals. So you are keeping your eye here, and by looking back into the circuit you are going to calculate your equivalent circuit resistance, and that equivalent circuit resistance is nothing but the voltage source internal resistance. So Thevenin theorem states that an active, as discussed, it states that an active linear and bilateral network containing several EMFs or several generators and impedances can be replaced by an equivalent circuit containing of a single voltage source. So it can be replaced by an equivalent circuit of single voltage source in series with a single resistance. So and that voltage source can be known as your Thevenin's equivalent voltage, let us say VTH, and the internal resistance of that voltage source is nothing but the ZTH, that is the Thevenin's equivalent resistance. So the rest of this circuit can be replaced by a single voltage source in series with the Thevenin impedance. Now putting it in other words, when a particular branch is removed from a circuit, the open circuit voltage appearing at the two terminals of the removed branch is your Thevenin's equivalent voltage, and the equivalent circuit resistance can be calculated by looking back into the open circuit terminals. So if we replace the rest of this circuit with a single voltage source, the voltage of that source is nothing but your open circuit voltage, and the resistance or the internal resistance of that source is nothing but the equivalent circuit resistance, which can be found by looking back into the circuit from two open terminals A and B. So now if I want to find the current IL through this load resistor or through the interested branch, I want to find the current, then I can connect my load resistor into this circuit. So here you are having your ZL, that is ZL, you can say this is IL, that is the IL is the current flowing through this circuit. So I can find my IL is equal to VTH upon ZTH plus ZL. So now if I apply my Thevenin's theorem for a DC system, then this Z Thevenin can be regarded as R Thevenin and this ZL as RL. So let us understand what does these terms mean. active, linear, bilateral. So an active network is nothing but a network which consists of active sources. It may be voltage source or current source. So whereas your linear network is a network in which parameters like R, L, C. So a linear network is a network in which parameters like R, L, C never change their magnitudes with respect to the variation in voltage or current or both. So the magnitudes remain constant, then they are said to be as linear network, or you can say if the circuit follows superposition theorem, then you can say it is a linear network. Now coming to the bilateral network is a network in which the parameters characteristics doesn't change with respect to the change in the direction of voltage or current. So the characteristics always remain whatever may be the change in the that is a change in the direction of current or voltage, whereas your unilateral, we are having other term, unilateral network always changes its characteristics with respect to the change in the direction of voltage or current. So now we have understood what Thevenin theorem basic definition is. We have understood how we got the open circuit voltage, that is the V Thevenin, and the equivalent circuit resistance Z Thevenin here. Now let us take an example here, but before going or proceeding to this example, we shall discuss some important sign conventions required for solving your Thevenin's theorem. So if I say I am having a particular branch, a resistive branch here, this is my resistive branch, and let us consider the current is flowing in this direction. So I am having here plus and here minus. So now this is my current direction, this is my resistive element. So now if I travel in the direction of current, so that is the direction of journey is in the direction of current, then the drop occurring in your resistive element can be taken as minus IR. That is positive to negative, there is a fall in voltage, thereby I am having minus IR as a voltage drop. Now if this is the same direction, that is the direction of journey, this is your direction of journey is in the same direction of current, then you are having negative drop. And if you consider or if you travel against the direction of current, so or you can say the opposite to the direction of current, then there is a rise in voltage, that is minus to plus. That means you are having the drop in the resistive element as plus IR. So this is a sign convention important to remember while solving the circuit Thevenin's theorem. And the other sign convention is while applying KVL, you always take the loop current to be flowing in clockwise direction. So whatever may be the actual direction of current, it is better to take the clockwise direction of current while applying KVL in the loops. So these are three important sign conventions. One is the current, that is a minus IR drop plus IR drop, and other is the clockwise loop current while applying KVL to the loops. Now we shall discuss this example and find the Thevenin's equivalent voltage and Thevenin's equivalent resistance. Now suppose if you are given a circuit like this and you want to know or you want to calculate the current flowing through this particular branch, and let us say we are having two terminal points A and B at this load resistor through which you want to find the current. So the first step we have to do for solving this network is draw the circuit by disconnecting this load resistor. So disconnect RL plus open circuit your current sources, open circuit current sources plus short circuit your voltage sources. So the first step is disconnect the load resistor through which you want to find the current, and next open circuit the current sources present in the circuit and short circuit the voltage sources present in the circuit. So we are short circuiting because the internal resistance can be assumed to be 0, and here we are open circuiting the current sources because the internal or the resistance of the current source can be assumed to be infinite. So they are considered as ideal current and ideal voltage sources, and thereby if we follow this step, so we are short circuiting this path, and here also we are short circuiting this path. So this has gone from our circuit. Now the next step is, what you have to do is, by looking back from these two open terminals A and B, we want to calculate the equivalent circuit resistance. So by looking from this point, if I see the so the 20 volt, we have short circuited the 20 volt, and you see 2 and 4 are in series, so thereby I am having here 6 ohm. Now 6 ohm is in parallel with 6 ohm, so let us write it here. 2 plus 4 is parallel with 6, it gives me 3. Now this 3 is connected in series with 3, so 3 plus 3 gives me 6, and this 6 here is connected in parallel with this 6, so this is parallel with 6, and I'll get here again 3, and this 3 is in series with 2 ohm. So 3 plus 2 gives me 5 ohm. So this is my R Thevenin. So R Thevenin we have calculated by disconnecting the load resistor, open circuiting the current sources and short circuiting the voltage sources, and by looking back into the open circuited network from the two terminals A and B, we have calculated the Thevenin's equivalent resistance. Now the third step is again replace the same circuit with the voltage source which are short circuited, and if you are having any current source, you have to replace the circuit with the voltage source and the current sources, and this resistor, the load resistor, should be disconnected from the circuit. Now if I want to, let us say this is my open circuit voltage VTH. Now if I want to know the VTH between these two terminals A and B, I want to know the current flowing through this branch definitely. So once I know the current flowing through this branch, that is the 6 ohm branch, 6 ohm resistor, then I can know the VThevenin, that is the open circuit voltage appearing between these two terminals A and B. For that, the third step is find the loops present in the circuit and apply KVL to the loops. So this is my one loop, this is one loop, and this is the other loop. So the current direction can be assumed to be clockwise. Let us say this is my I1 and let us say this is I2. So whatever be the actual direction of current, irrespective of the actual direction of current, we are assuming it to be clockwise for our KVL rule. So that is the Kirchhoff voltage rule. By applying the Kirchhoff voltage rule, we have seen how the sign conventions are going to vary. So by knowing these sign conventions, let us apply the KVL rule to this loop. So for loop 1, I am writing my KVL. For loop 1, if you see, if I travel from this path to like this, then minus to plus, there is rise in voltage. So I am writing plus 20. Again here, if I say this is my plus, because the current is flowing like this, this is my plus, plus, minus, this is plus, minus. So again plus to minus, there is fall in voltage. So minus 2 into I1. So we are traveling in the same direction of, that is the current direction. We are traveling the same direction as the current is traveling or the current is flowing. So again here I am having minus 4I1 and here minus 6I1 is equal to 0. This is my loop 1 KVL equation. Now for loop 2, similarly, the current is flowing in the clockwise direction, so this can be plus minus, so this will be plus minus. So here we have written a mistake. You have noticed here the current I2 is also flowing through this branch and the current I1 is also flowing through this 6 ohm resistor. So here what I have to do is I have to write 6 into I1 minus I2 is equal to 0. Again, if I write KVL in this loop, I am having minus 3 I2 minus 6 I2 and plus to minus, there is falling voltage, that means minus 25, and here plus to minus. So in this loop consider I2 is greater than I1, and in this loop consider I1 is greater than I2. So by considering I2 is greater than I1 here, I will say my current is flowing here, that is plus to minus, and there is a falling voltage, so minus 6 into I2 minus I1 is equal to 0. So we have got the two equations and we are having two unknowns. So if you solve those two equations, two algebraic equations, you will get I1 is equal to 1.041 amps and your I2 is equal to minus 1.25 amps. So the actual direction of current we have got from here, that is the actual direction of current is from like this, your I2 is flowing like this. So it is opposite of our earlier considered direction. That is why we got the point, that is why we got the value, that is minus 1.25. So but the I1 is in the same direction as we have considered earlier. So the current through this 6 ohm resistor is, you are having 2.291 amps. So now we have got the current flowing in this branch. Now we can easily find the Thevenin between these two terminals A and B. So again, you start your journey from A to B by traveling through any of the branches, any of the path branches. So you can travel from here to, from A to B like this, or you can travel from A to B like this, or you can travel from A to B like this, and whatever the voltage you face during your journey is nothing but your Thevenin. So let us take the simplest path is this path from A to B. So in this branch, as it is open circuited, there is no current. So if I write KVL to this, then I am having 2 into 0, and if I say the current is flowing in this direction but my journey is in this direction, so I will be taking it as plus 6 into 1.25, and here there is a fall in voltage, that is a plus to minus, so I am considering it as minus 25, and this again, if I draw this Thevenin like this, again minus to plus, this will be plus VTH is equal to 0. So from here you can find your VTH is equal to 17.5 volts. So from this we got the Thevenin and the Thevenin. So from here I can write IL is equal to 17.5 upon my Thevenin is 5 plus the load resistor, the value is 10. So this gives you 1.66 amperes. So we have found the Thevenin, Thevenin and the load current. So this Thevenin's equivalent circuit can be replaced with Norton's equivalent circuit by simple, just you have to calculate the I Norton is equal to Thevenin by Thevenin and placing the Thevenin in parallel with the current source. So your R Norton will be equivalent R Norton circuit will be like this. This is your Thevenin, this is your R Norton. For Norton circuit, this is R Norton, and this is I Norton, where your I Norton is calibrated in this way and your R Norton is placed in parallel with the current source. So the practical application of your Thevenin theorem is, it can be, so here the load can be varied. You can take any type of load like a bulb or fan load, and you can check the voltage and the current at this juncture. And the other application is, now once you get this equivalent circuit, you can, as if your aim is to obtain the maximum power from the source, then you can make your ZL is equal to Z Thevenin, thereby you can obtain the maximum power. And the third application is, so if say some fault has occurred here, and the voltage at this point is V, and from this point you are having Z Thevenin, and by knowing the Z Thevenin, that is the equivalent circuit impedance, and V, you can calculate the fault current in power system analysis. So this is all about your Thevenin's theorem. I hope you understood well. Please subscribe to the channel. Thank you.